For any assignment-related queries, call us at +1 678 648 4277. You can mail us at info@statisticshomeworkhelper.com or reach us at https://www.statisticshomeworkhelper.com. Chapter 1-1. 1. Exercise 1.3 in text. 2. Exercise 1.9 in text. 3. Exercise 1.13 in text. 4. Exercise 1.20 in text. 5. Exercise 1.26 in text. statisticshomeworkhelper.com. Solution to exercise 1.3. 1.3. A. Since A1 and A2 are assumed to be disjoint, the third axiom of probability says that since m equals 1 ohm equals infinity m equals 1 am, the term on the left above is 1. Since PRAM equals 2 minus m minus 1, the term on the right is 2 minus 2 plus 2 minus 3 plus equals 1/2. Thus the assumptions about the probabilities in the problem are inconsistent with the axioms of probability. B. If the third axiom of probability is replaced with the finite additivity condition in 1.3 of the text, then all we can say from the modified axiom is that for all n greater than or equal to 1, the sum on the right is simply a number that is increasing in n but bounded by 1, so we go to the limit n infinity. statisticshomeworkhelper.com. Unfortunately, we have no reason to assume that the limit on the left can be interchanged with the probability, and in fact the essence of the third axiom of probability is that this interchange can be made. Thus this cannot be used to show that the assumptions about the probabilities are inconsistent with these modified axioms. This suggests, but does not show, that the assumptions are inconsistent with the modified axioms. With the modified axioms, it is conceivable that some probability gets lost in going to the infinite union. We apologize for assigning this problem, since it does not provide a good example of the need for countable additivity in the axioms. Showing this need correctly appears to require measure theory. Solution to exercise 1.9. A. The maximum of NIID random variables is less than or equal to x if and only if, IFF, each of the individual random variables is less than or equal to x. Since fx(x) is the probability that any given one of the n variables is less than or equal to x, fx(x) n is the probability that each is less than or equal to x. Thus, letting max equals max, x1, x2, x3. statisticshomeworkhelper.com. B. Similarly, the minimum, min equals min, x1, x2, xn, is greater than xiff each variable is greater than x. Thus, C, letter equals max minus min, see figure. We start by looking at the joint probability of max and min by the same technique used in A and B. In particular, max less than or equal to x and min y iff y she less than or equal to x for 1 less than or equal to I less than or equal to n. Thus, PR max less than or equal to x min y equals fx x minus fy y n. From the figure, we see that statisticshomeworkhelper.com. Assuming that x has a density, this simplifies to solution to exercise 1.13, A. Since x1 and x2 are identically distributed, PR x1 x2 equals PR x2 x1. Since PR x1 equals x2 equals 0, PR x1 x2 equals 1/2. Again, using the symmetry between x1, x2, and xn. C. Let's define an equals 1c. Let's define an equals 1 IFFXN is a record to date. Then the expected number of date. Then the expected number of record to date that occur over the first M trials is C, letter equals max minus min, see figure. statisticshomeworkhelper.com. The expected number is infinite as M infinity. Solution to exercise 1.20. A. Suppose z equals x plus y mod 2. That is z equals 0 if x equals y and z equals 1 if x equals y. Then, if x and y are independent, there are 4 joint sample points: x equals 0, y equals 0, z equals 0, x equals 0, y equals 1, z equals 1, x equals 1, y equals 0, z equals 1, and x equals 1, y equals 1, z equals 0, each of which have probability 1/4. All other combinations have probability 0. Each pair of random variable is independent, but the set of 3 is not. B. For the example above, the product xyz is 0 with probability 1, and thus xyz equals 0. On the other hand, EY equals 1/2, 3. Thus pairwise independence is not sufficient for joint independence of all the variables. Solution to exercise 1.26. The algebraic proof of this is straightforward. Note that the set of x satisfying fx, x, less than or equal to y, i.e., x, fx, x, less than or equal to y, is the same as the set of x for which x less than or equal to fx minus 1, y. See figure. Thus, statisticshomeworkhelper.com. To see what is happening more clearly, consider PR, y less than or equal to y less than or equal to y plus delta, see figure. The event y plus delta is the same as the event f minus 1x, x f minus 1x, x plus delta. But from the figure, this event has probability, y plus delta, minus y equals delta, meaning again that y is uniformly distributed over 0, 1. Note that the result does not hold for a discrete random variable. For example, if x is a Bernoulli random variable with px, 1 equals p and px, 0 equals 1 minus p, then statisticshomeworkhelper.com. From this we can see that the random variable y equals fx, x, can only take the values p and 1. Since x can only take on 0 and 1, so y couldn't possibly be uniformly distributed between 0 and 1. statisticshomeworkhelper.com